Okay, so we're gonna do some acceleration calculation examples. Well, some of them involve acceleration. And because a lot of what I would normally do right now is in the classroom, I'd be doing a bunch of examples on the board, so I thought it's better to see them right here. Okay, so I've got 5 examples I'm going to do right here, and you can see how they're done. First one, calculate the velocity if a motorcycle starts at a position of 25 meters and moves to a position of 388 meters in 22 seconds. So clearly these are both positive numbers, so that means the motorcycle is moving in what is considered a positive direction. And here is the equation. Obviously it says velocity, but this is the average velocity. So we want the delta x and the delta t. This is the one we're using right now. Okay? So in order to determine delta x and delta t, well, we actually need these. And I didn't have those here. So delta x is x final minus x initial. Remember, this is position. Okay? X is position, like assuming that you're moving along one axis, right? So what is my xf here? Which one is xf? Okay, so let's get my delta x equals xf, which one of these comes later? Oh, 388 meters minus x initial. Oh, we started at 25 meters. And then, of course, if we subtract these, we get 363 meters. Okay? So that is my delta x. So now we have delta x. What about my delta t? Well, we're assuming here that we're starting at time equals 0 because it says in 22 seconds. So no matter where we started, we're winding up 22 seconds later. So we're assuming we're starting at time equals 0 seconds and ending at time equals 22 seconds. Or actually, we could have started at time equals 100 seconds and ended at 122 seconds. It doesn't really tell us that, but we might as well assume that we're starting at 0. It makes it easier for us. So then we've got delta t, because delta t is equal to final time is 22 seconds minus initial time, which is going to be 0 seconds. It's not even listed here. And that, of course, equals 22 seconds. So now, to get my average velocity, now notice on velocity, I put the line there. Because there is a difference in your instantaneous velocity, and I was considering going into that, but we might not be going into that too much anyway. Notice on acceleration, this is actually average acceleration too, but I'm a little sloppier with the line there. Technically, there should be a line there just as much. Okay, so then, which one goes where? Well, that is my delta t, goes on the bottom, 22 seconds. This is my delta x, goes on the top, 363 meters. So now let's bust it out on a calculator. Numerator, 363, divided by denominator, 22, equals, so my average velocity equals 16.5, I'm going to make this darker, 16.5, oh, what units would I have? Well, meters divided by seconds, it would be meters per seconds. That line, so seconds are in the denominator here. And then, of course, that is my answer, so I probably want to make a clear box around it so that that is clearly shown as my answer. Okay, so that was a velocity calculation. Let's see what the next one is. The next one is an acceleration question. So let me change out this paper. I'll put on a new paper right there. Oh, that works. That works pretty well. Okay. So we're doing an acceleration question. So think about this one now. If a runner is moving forward, so we've defined that direction as moving forward. Remember, acceleration is a vector, just like velocity is a vector. Speed is a scalar, as we mentioned. Velocity is a vector. Okay, running forward, going from 1.0 meters per second to 5.0 meters per second in the same direction. So let's say they're going forward or to the right. We often choose this direction as moving forward because it's the direction we read. Okay, so when usually we're talking about the front of an object moving forward, right? Or in this case, a runner. So what we need for acceleration is delta v over delta t. But again, we need this one, don't we? Because if I'm going to get my delta v, okay, if I'm going to get my delta v, I need delta v equals, okay, maybe I'll use a darker pen. Delta v equals v final. So which of those is my final velocity? Which one? Which one happens second at the end? Oh, the 5.0. So remember, it's final, that's darker, meters per second. Let me darken this one too then as well. Okay. It's the final minus initial. This is initial because it was earlier. It was where we started. Okay. So final happens last, initial happens first. Okay, and what does that equal? Well, 5.0 minus 1.0, I don't really need the calculator, do I? Do I? 5 minus 1? 4, and then the 0.0 because we know it that accurately, meters per second. So now I've got my delta v equals this, okay? So what else do I need? I need my delta t. Well, again, it says in 10 seconds. So when did this start? Well, we might as well say we started at 0 seconds. So then for my, once again, for my delta t, okay, your final time was 10 seconds minus initial time, ti, okay, minus ti, which would be 0 seconds. So again, subtracting 0 doesn't change anything, and you have 10 seconds. So to get my acceleration, and technically it should have an average acceleration, okay, well then it equals, here's the fraction, and it equals, on the top we've got my, where's the blue? Okay, here we go, 4.0 meters per second, and on the bottom we've got 10 seconds. So you might wonder why acceleration, why does it have the units that it has? Well, because look at how we get it. We're dividing a velocity, meters per second, by seconds. Okay, so you might say, well then it's going to be meters per second over seconds. Okay, but then this is in the denominator just as much as this is, so that equals meters per second squared. That's how we wind up with that unit. Okay, so then if I wind up, I'll just put this one in black. So my acceleration equals, well, what's 4 divided by 10? 4 divided by 10, it just moves the decimal place. Divided by 10 moves the decimal over 1. So 0.4, and then meters per second squared. Those are the units of acceleration. And this time I'm going to circle it, just make a nice oval around it. Okay? So you might be disappointed by some of your accelerations, because it turns out if an acceleration is really high, then things get out of control really quickly because it's sort of a geometric growth. So you might wind up saying, oh, that doesn't look like too much. You know, these seem like good numbers, but yeah. Well, that's the way acceleration often is. It often isn't a very impressive number, but that means that will accelerate. You'll see why. The acceleration builds on itself, okay? So there we go. The next one we're going to do is going to be, I'll just peel off the paper and then flip it. This one is done. Then the next one we're going to do is going to be this one. Oh, it's very similar. Look, very similar. I just modified the same question, right? Okay, so calculate the acceleration if a runner is moving 5.0 meters per second in a forward direction, but is moving 1.0 meters per second in the opposite direction 12 seconds later. Okay, so one way to write this would be with positive and negative signs, but you've got to decide where to put them. So we usually define the direction that we're going as positive, at least the way it's initially going. So let's define that one as positive. That would mean the other one would wind up being negative. This is where it gets a little tricky. So it's just like this one, and again we need this. So we need the delta V. We need our delta V. So delta V. So which one is final. Which is the final one? Oh yeah, this is the final. But even though it's smaller, it's our final one. And don't forget the opposite direction. So if we're defining where the way we started is positive, this will actually be negative, negative. So negative 1.0 meters per second. You can definitely have negative velocities, definitely, because it is a vector. Okay, so it depends on the direction it's going. If we define one way as positive, certainly the opposite direction would be negative. Okay, and then it's still minus, right? Minus the initial, the minus the VI, which is 5.0 meters per second. Well, this is a negative and this is a negative. Put them together, or you could say a negative minus a positive, if you want to think about it that way. Okay, so we know what's going to happen here, right? So if I put in 1 with a negative sign minus 5, I get 6, negative 6.0 meters per second. So because they're both have a negative sign in front of them, okay, it adds to a, let's say, a negative number with a greater absolute value. It's really hard to talk about negative numbers, okay, whether they're bigger or smaller or more negative. It's just tricky to talk about. Okay, and then what about my delta t? Well, just for the same reason, let's just do this faster now. You know, that was my final time, 12 seconds. What was my initial time? Well, we started at 0. We just chose that, and that equals 12 seconds. Time will not be negative. Time is going to be positive. Okay. So then, what's my acceleration? I'll just use the black one. It shows up better. Average acceleration actually equals, and I'll put the bar here. So now we've got a negative number that goes on top. Okay, for the delta v, it's a negative 6.0 meters per second. And on the bottom, I've got 12 positive 12 seconds. So when we divide those, well, a negative divided by a positive equals a negative. So we've got our acceleration equals negative, and 6 divided by 12, well, that's just like 1/2, isn't it? 6 over 12, 0.5, and then meters per second divided by seconds. If you want to just do it for sure on the calculator, if you just feel like double checking, yes. And then you get meters per second squared. Meters per second squared. And again, that's my acceleration. So it's a negative acceleration. The earlier one, okay, the earlier one, we didn't put it, but we could have put a positive sign here. But usually we assume if we see a number that doesn't have a negative, we just assume that it's positive. That's the way that we write our numbers. So this is an acceleration in the other direction. So it is possible to be moving in one direction, but accelerating in the other direction until it stops you and eventually turns you around. In this case, it just started turning it around. And if you had waited longer, it probably would have been going faster in the opposite direction as long as the acceleration continued. Okay? Okay, so let's see what the next one is. Okay, so we did a velocity one. We did 2 acceleration ones. Let's see what the next one is. Okay. Oh, interesting. This is how long does it take a car to travel 5 kilometers if it starts from a standstill and accelerates at 8 meters per second squared. That's an acceleration number. So this is an interesting one because it looks kind of tricky, and it could be really tricky because it involves this equation. And because it involves this equation, you might think, oh man, if I've got a t and a t squared, well, I might have to use the quadratic equation. Oof, let's see. But maybe not. Well, we'll see. We'll see how this works out. All right. Now, sometimes you do need to use the quadratic equation to solve these. And of course, if one of your numbers, you get 2 results from a quadratic equation, and one of them is probably not the right answer, so you can usually just use common sense to figure out which one is right. But then a lot of times we can avoid it because you'll see what happens in this one. Okay, so what do we need for this? Well, let's just write out this equation and let's just substitute for what we have. By the way, x would be like where our position, where we wind up, okay? And then xi would be our position where we started, okay? Plus your initial velocity times time plus 1/2 at squared. So you could do 1/2, this is the way we normally write it, then a t squared. Now, you could also put at squared over 2. but this was just done to put it all on a straight line. So that is 1/2, or 0.5. Okay. So let's see, what numbers do we have here? Let's just substitute them. 5 kilometers. How long does it take a car to travel 5 kilometers? Well, that will be my distance that I'm traveling. That'll be my x. 5 kilometers, though, wait a second. This is in meters. I better put that into meters. So how many meters are in a kilometer? Kilo, the prefix kilo, means 1,000 times bigger. So what I have to do is take my 5 times 1,000, and of course that's 5,000. So that's 5,000 meters. Be very careful if you get things in kilometers. You can actually do accelerations entirely in kilometers if everything is in kilometers, but it probably won't be because a lot of times your accelerations are not. So it's probably better to turn them into meters just to be safe. And by the way, the conversion between that, if you want to see the conversion, you'd have 5 kilometers, and then I would multiply it by 1,000 meters over 1 kilometer equals 5,000 meters. That's the result. Okay, and I guess I'll put a little comma here so it's clear. It's 1,000. Okay. Some countries, they put a decimal there, making it increasingly confusing. Oh well, we don't do that. Okay, so then my xi. What is my xi? Well, let's see here. If it starts at a standstill, you know, it doesn't tell us any xi, so why don't we just assume that we're starting at our reference frame of 0? Do you know what happens? You start at 0, then this becomes a 0. Boop, that's a 0. And then what's my initial velocity here? Oh yeah, standstill. So my initial velocity is also a 0. So it's plus 0 times t. Oh, is anything times 0 is 0, so that disappears. You don't have to worry about that. Oh, great. So the great thing about this is sometimes some of these terms disappear. So even though we have this whole equation, really because it's just the acceleration, we're losing these terms. They've disappeared because of 0. And now we just have the 1/2 at squared. So it's 1/2, I'll put the 1/2, and then I'll put parentheses for my acceleration. Oh, it's 8 meters per second squared. So 8 meters per second squared is my acceleration. And what's my t? What's my t here? Does it give me a t? No. So t is what I am solving for. So what you do in a situation like this, and it's t squared, what you do in a situation like this is you work all this out, get rid of it, and then you have t squared, then you take the square root of the other side. Okay, so let's write this again. Now we're down to 5,000 meters equals 1/2 times 8, well that's just 4 meters per second squared. Let's put that in parentheses, t squared. So whenever you have a variable that's attached to something, you have to isolate the variable. It sounds really mean to isolate variables, but it's actually very nice. It gets them all by themselves, which is what they like to be. Okay? So even though isolating a variable sounds mean, it is not mean. So what we're going to do is get rid of what is next to it. If the thing next to the variable is multiplied on, we have to divide it off. If it is added on, we subtract it off, we do the opposite function. Okay? So we've got to divide this side by 4 meters per second squared. Okay? But then we can't just do something to one side of an equation, of course. If you do something to one side, you best do it to both sides, or it's no longer an equation. It's no longer true. Okay, so when we divide 5,000 by 4, 5,000 divided by 4, what do we get? 1,250, right? And then when we divide over here, what happens? Well, the 4's cancel, the units cancel, and we are left with t squared. Oh, I forgot to see what happens with the units here. Okay, well, meters divided by meters, they disappear. And then this is the tricky part. When you divide by per second squared, it flips it back over, and you wind up with seconds squared, S2, which is good because times squared is going to be seconds squared, isn't it? And then the last thing I have to do is to solve for t. I have to take the square root. I'm running out of room here. I'm going to write the square root of 1,250 seconds squared equals t. And then let's write it over here. T equals, when I take the square root function, there's that little square root radical. I get 35 point, And then you don't want to keep all of these digits. You want to probably keep, like, let's see what kind of numbers we've had here. Probably don't keep too many. Maybe one more, two more digits. I'm just going to keep 35.4. And then, of course, the square root of the unit second squared would be seconds. Okay? Second squared, if you take the square root of it, you would have seconds. And then what I like to do whenever I take a square root, just to be safe, make sure that that's right. Just do times, and then it's times itself, equals. Make sure you get back to a number that at least is rounds to this. Okay, because things can go wrong on calculators. So just this number times this number should get us back to this. Seconds times seconds gets us back to seconds squared. So now you could go through and plug this back into the equation. One good way to check is plug it back into this equation, put that in as your t right there, and see if it gives you that. Okay? So as you know, let's see, if we take 35.4, I'm just going to keep it like this, times 35.4 is going to give me 1,253 now because of rounding, seconds squared. And if I multiply that times 8 equals, divided by 2 equals, and then, of course, this would be seconds squared times meters per second squared. The second squared would cancel. We'd have meters, and it gives me 5,012. That's because of rounding. Okay, so just keep in mind, it's pretty good. That's a good way to make sure you did it correctly. So sometimes because of rounding, because squaring amplifies mistakes, amplifies error. So maybe I could have kept one more digit, but it was being a little disingenuous because of the amount of information we had going in. Okay, look at that information going in. Really keeping things to the hundredths place, thousandths place is usually not done. They're not significant figures. Okay, guys, so that's this one. Let's see what the next one is. The next and final question, I believe, that I'm doing right now is, what would the final velocity be for a truck that is already moving forward? Oh, this is a two-part question. Let me do it this way. I forgot that I have this two-part one here. Okay, this is a two-part question, but it's our last question. All right. What would be the final velocity, that's this, for a truck that is already moving forward at 20 meters per second at time equals 0 seconds. So this time it makes it very clear when we're starting, okay? Then accelerates forward in the same direction that it's moving, forward, at 5 meters per second squared for 7 seconds. Okay, well, here's the equation for final velocity. It almost fits in there. Okay, so this isn't so bad. This looks bad, but it's not. Not bad at all. Much easier than this last one. Okay, so let's see. What numbers do we have here? We want to know final velocity, so we're solving for VF. Okay, do I have my VI? What was my VI? That was my initial velocity. Oh yeah, this at time equals 0, that must be my initial velocity. 20 meters per second, that's the velocity, right? And moving forward, and so it's going to be a positive, and the acceleration is in the same direction. It's also positive. These are both positive numbers. We don't have to show them. We don't have to show the positive there, but that's a positive velocity and a positive acceleration. And 5 meters per second squared, that's my A. I'll put that into some parentheses. And for 7 seconds. 7 seconds. So actually we have everything we need on one side. We just plug in the numbers and get our result. Boom. Okay, so again, well, 5 times 7 is 35, right? 5 times 7, okay, that gives us 35. Now it was meters per second squared, but then we're multiplying times seconds, so that cancels out that second and one of the ones in the denominator, so that puts it in the same unit. Once it's in the same unit, well then you can add it to the one before it, so this isn't really hard mathematics. So 20 plus 35, right? Okay, 55, add the 20, get 55 meters per second. So that's not too bad, right? That's actually pretty easy. So that's the answer for the first one. But there's a second part. What would the displacement of the above truck be from time equals 0 to time equals 7 seconds? Okay. Oh, wait. Now we really get to use this one. The reason I gave the second part now that I remember that I did that, is to use this guy. Okay, so what is my initial position? So we're solving for, let me do this one in a different color. Okay, so we're solving for x. Okay, what's the displacement? That's like where you're going to wind up. We're defining where we're starting as 0. So this will be like where you wind up. Okay, so my initial position, oh yeah, we're starting at, it's already moving forward, but we might as well, even though it's already moving, we might as well define where it was at 0 seconds as 0 position. So if xi is 0, that makes things easier. Okay, and then we need our initial velocity. Okay, or my initial velocity, not my final velocity. Okay, my initial velocity. Interesting, interesting. And my initial velocity is 20 meters per second. So you might have been tempted to use that. You're like, hey, I just went through all the trouble to get this, but that's not what I put here. I actually put where it was starting, because the 20 meters per second is how fast it's already going when we're at time equals 0. So let's say it's already going, and then boom, that's 0. It's already moving. Okay, and it's going to keep having that velocity. That's going to be a component of what it does afterwards. So that'll be changing its position even aside from the acceleration. Then the acceleration is going to go on top of that, or if the acceleration is negative, it will subtract from that. But that's got to be included. And then what's the t? What's the amount of time that we have here? Time is what? From 0 seconds to 7 seconds? Okay, so you could think of it as how many seconds have elapsed, or think of it as a delta t, right? 7 minus 0, 7. So my t is 7 seconds. Okay, I'll just put the time in red. Then that's going to be plus 1/2. What's my acceleration again? Right there. Plus, I'm going to put the acceleration, 5 meters per second squared, in parentheses. And then it's going to be t squared. Well, again, we just said t is 7 seconds, but it's squared. Be careful. That is where people often make a mistake. Sometimes with the 1/2 and sometimes with the squaring. Okay, so now we just got to go through and crunch all this. Okay, so well, we can leave the 0 out. Okay, we don't have to worry about that one. That's gone. So we're going to do x equals, and then we've got 20 times 7. Sounds like 140, right? 20 times 7, just being careful. 140, so meters per second times seconds. So the seconds will actually cancel, and you'll have meters, which is good because we're going to wind up with a displacement or a position, which is going to be in meters from where you started. Okay. Plus, so it's going to be plus 1/2. Well, you know what? Let's multiply these together first, and then we'll deal with the 1/2. Okay. So first of all, 7 has to be squared. We have to square those. So 7 squared is 49. 7 times 7 equals, seconds times seconds is seconds squared. So we're going to have 49 seconds squared. That's what that equals. And then since we did that separately, we might as well take this 1/2 times 5. You could do it at any point because of order of operations. It doesn't matter when you divide by 2, as long as you do divide by 2. Okay, so it'll be, say, 2.5, and then that doesn't change the unit. Meters per second squared. Okay. And then, of course, when we multiply here, I might have to scoot this upward a little so you can still see it. I'm going to scoot this one up a bit. Make sure you can see the next step. I'm going to slide it up a bit. Okay. And this is the one we're working on. Okay, so if you multiply the 2.5 times 49 equals, and then what we get here is 122.5, and then again, meters per second squared times seconds squared, the second squareds cancel, and you wind up with meters. So now we've got 140 meters. Okay, x equals 140 meters plus 122.5 meters. Well, I've already got the 122.5 on here, so I'm going to hit plus 140 equals, so then I'll write it over here, x equals 262.5 meters. Okay? And we want to circle that answer, put a square in it so it doesn't get confused with all the other stuff on here, all over the place here. And I guess I could have done that a little more neatly. But the point is that everything had better turn into meters. And you can't really add them till the units are the same. I should have mentioned that here. The reason we can add these was because the units were the same. You couldn't have actually added meters per second plus meters per second squared. You couldn't do that. They're different units. But when the units become the same, then we can add them. That makes things easier. And notice, don't forget to square. That's a big little slip up that people sometimes do. They forget to square the t over there. That makes a huge difference, obviously. And then the 1/2, another way to write this part is like you put at over 2. You could do it that way. At squared over 2, excuse me, at squared. And if you want to know where that comes from, well, think about calculus. You think about differentiating, integrating in calculus. You can sort of see where that came from. You get the square there and the 2 underneath. It kind of comes out of that. Okay, guys, so those are the examples. That should be enough for the level we're doing for this particular section up until our quiz, which of course is a motion quiz. There'll be some of this, maybe not everything that's on here will be on the motion quiz. And some of this will actually be on the next assignment. So now you get some examples to look back at. Okay? That's it. Bye-bye.